you may know that, some people from the IPC, we were visiting ICTP a few years ago. So it was a pleasure really to know a little bit more about the center, because to me, this is really an exceptional center. I mean, a singular one in the world for the quality of the science that they do, but also because of other missions that they also assume as part of their activity of their mission. So Ali himself, he works in the part of in the section of condensed matter physics, right? Ali, if you allow me to say that, he's a citizen of the world, right? He was born in Tanzania, but he grew up in Kenya, but then he made his university studies in the US, right, in Purdue University. Then you went to Ohio State University, as far as I remember. Yeah. Then you moved, let's say, for a postdoc to Switzerland, to Europe, to work with Michele Parinello. Yeah. And now he's in Trieste, so he has been traveling all around the world and working in different places of the world. And we are lucky enough to have him here today, these days. And I hope this is the very first of many visits or a continuous link between the IPC and ICTP. So Ali, thank you very much for the visit.
Great. Thanks very much, Ricardo, and thanks very much to all of you for the warm invitation. It's also nice to see some familiar faces, Emilio, of course, and Yovar, who I know through the ICTP networks. The title of my talk today is Chemical Continuum, Overcoming Discrete Notions Underlying Fluctuations in Liquid Water. Before I start on the science, I just wanted to tell people a bit about where I come from, in case you don't know. So what is the ICTP? The ICTP is actually the Abdus Salam International Center for Theoretical Physics. It's an important thing to remember. Abdus Salam was a Nobel laureate who founded the institute. Now it's going to be a 60th anniversary next year, I believe. And he had this really incredible vision, which is that he believed that scientific thought is the common heritage of mankind. And he started this institute with the idea that it would be a place that would nucleate people from developing and developed countries to really foster science, research, and education. And one of the key missions of our institute is trying to close the north-south divide in research and science. And actually, so this picture here is now of our new director, Atish de Volker, who's also a high-energy physicist. So that's a bit about the institute. We're located on the Gulf of the Adriatic Sea. Trieste reminds me a lot about San Sebastian in many ways, except for the rain. But I learned over the last 2 days that San Sebastian's a place where you just take your umbrella and just move along. Okay, very good. So I want to start by showing you this picture, and I'll give you some time to look at it. But I think it sort of summarizes a bit for me both the perspectives and the challenges that data science offers to the physical sciences. Okay, so let's break this down a bit. So in my opinion, a lot of our understanding, interpretations, models that we develop in the physical sciences, physics, chemistry, even biology, rely on looking for simplicity. So projections. So in this case, you have these two people here smoking a cigar and drinking a cup of wine. But these projections come from projections of much more complex and high-dimensional data, which is reality, and that's the reality in this case. I don't know if this picture is true or not, actually, but the message still remains. And what I want to try and do over the course of my talk today is tell you a bit of some of our work that we've been doing over the last couple of years, and trying to understand this complex mess of fluctuations in water. And by the way, if there are any questions during my talk, please stop at any moment. I'm happy to just have discussions as I move along. And so one of the big focuses of the research in my group is basically to ask, is water a silent spectator in physical chemical processes, or is it an active participant? And so a big part of that is trying to understand the different types of fluctuations, which I will get into as we move along. And so I know that there's probably a rather diverse audience of people here, but whether you're coming from a more chemically inclined background, thinking about chemical reactions in water, or you're coming from a more soft matter physics background, where you're thinking about, polymers, proteins folding, proteins aggregating together. Regardless of this, all these processes happen in an environment, and typically in an aqueous environment. And so what we try to do in my group is essentially try to use different types of atomistic simulations. I will tell you about them as we move along, combined with what we think of as smart data mining. I'm not sure if it's smart or not, but you can be the judge. And sort of try to bridge this gap now between trying to reveal new physics and chemistry in water in different contexts. And so that's what I will try to share with you. And so you may ask, well, what more is there to learn about water, right? It seems like such a simple thing. And why are fluctuations in water difficult to understand? And so just to calibrate you and build your intuition a bit, this is showing you a movie from a molecular dynamic simulation of liquid water. And if you stare at it long enough and you try to understand what's going on, there are basically three things that, in my mind, make sort of the understanding of fluctuations in water difficult and challenging. One is that you have density fluctuations that are happening on different length scales and time scales. And because water is a dipolar liquid, so there are directed hydrogen bonds. And so there's an underlying topology of the hydrogen bond network that evolves, again, on different length scales and time scales. And coupled to these density and fluctuations in topology is also how the electronic charge responds and fluctuates during these fluctuations. And so a lot of the controversies regarding water and sort of confusions about water boil down to confusions about what length scales and time scales of processes are we talking about. Okay, and so just to give you a feeling of a bird's eye view of what I referred to in the beginning of my talk, which is discrete notions. Discrete notions or concepts are sort of at the heart of many models and suggestions or interpretations in physics and chemistry. So one of the most popular ones, which is a source of a lot of intense emotional debate amongst many physicists and chemists at the moment, is what is the local structure of water? And so you'd think we would have figured this out, but apparently we haven't. And so there's been a huge raging debate for many decades on two-state models of water. So is water a mixture of two liquids? And people think about them in terms of these fluctuations between high density liquid and low density liquid. Okay, so that's an example of something. I will come back to this during my talk. So that's one example of a discrete notion. Another one, probably more popular in the chemistry community, is, okay, you take a hydrogen atom, you pull out an electron, you get the proton, and now you put the proton in water. This is the excess proton in water. And you ask, well, what is its molecular structure? Okay. And so there's been a raging debate, again, spearheaded by these two people, Eigen and Zundel. And so there are people who've been claiming, well, the excess proton is an Eigen, and there's another camp that says it's Zundel. Okay. And these two sort of discrete notions are at the heart of how people interpret spectroscopy in real experimental measurements. Okay. Another one that I guess some of you may also connect with is classifications in chemistry, chemical physics of is a solute hydrophobic or hydrophilic, right? And what I will try to suggest towards the end of my talk is that these sharp distinctions between what is hydrophobic and hydrophilic are, I think, a bit dangerous, and they don't sort of reveal the true continuum of interactions that actually exist when solutes are in water. Just to give an example of this, I won't have time to get into this during my talk, but in chemistry, if you ask a chemist, what are fluorophores? What are things that fluoresce or emit light? And typically the picture is that it's mostly aromatic amino acids, aromatic groups, things that look like benzene that are able to absorb light and emit, so fluoresce. And so just to tell you that basically these discrete notions of how we understand and interpret phenomena in both physics and chemistry are at the heart of a lot of our activity. And this is the thing I just want to perhaps challenge over the course of my talk. Okay, and so getting more into more specifics, over the last decades, there have been numerous descriptors or order parameters that have been developed in the physical sciences to understand what the structure, for example, of water is. And one of the most popular ones is this one developed by Pablo de Benedetti. It's called the local tetrahedrality measure. So what it does is you say, okay, I look at a particle in the center, and I ask, I look at my nearest 4 neighbors, and I ask, how different is this from an ice-like environment? Okay, so this is it's a measure of tetrahedrality. And for whatever reason, you will see later as we move along, people decide to focus on only the nearest 4 neighbors, and not the nearest 5 neighbors. Okay, so just keep that in mind. Another very popular one in the chemistry community are hydrogen bonds, right? Hydrogen bonds are kind of the dogma of chemical interactions because they're quite ubiquitous. And a very popular set of descriptors are hydrogen bonding criteria that use geometry to decide what is interacting or not. So for example, hydrogen bonds are when the distance between 2 waters is less than 3.5 angstroms and less than 30 degrees. But if the distance is 3.52, it's not a hydrogen bond. If the angle is 31 degrees, it's not a hydrogen bond, right? Why? Right? And why this becomes important is because it of course affects people's interpretations of states and structure. So in all these things, what you see we are doing is dimensionality reduction. That's easy to do, it's simpler. And when we do this, we have an uncontrolled information loss. We don't really know how much information we're throwing out when we do these types of projections. And one thing that I will try to underscore as I move along is that chemical imagination, which a lot of these sort of concepts come from, has its limits. And it has its limits because when you're dealing with fluctuations in a liquid like liquid water, there are highly cooperative and collective processes going on. And so you have to move beyond local descriptors, okay? Okay, and so just to build your intuition a bit about a concept that I'm going to come back to during the first part of my talk, I just want to introduce to this notion of something called the intrinsic dimension of any data set. So if I take random points in 3 dimensions in a cube, I generate them, and I ask you, how many directions do I need to describe the relevant fluctuations? You will naturally tell me 3, right? There are 3 directions that I need to describe the fluctuations in the system. However, I can also generate data where there are correlations between the data, and the data might lie on a sphere. And I can then ask the question again, what is the intrinsic dimension of this data set? And you will tell me it's 2, right? I need 2 degrees of freedom to describe the surface of a sphere. And so this has an important sort of relationship with physics in terms of entropy, and I will try to allude to this as we move along. But correlations in data generally reduce the intrinsic dimensionality, which is why, we sort of, when we construct these types of order parameters, we are relying on intrinsic correlations to say, okay, I can get away now with describing the system with these reduced set of order parameters. Okay. And so the question we put ourselves to was to ask the following. So can we define or estimate the intrinsic dimension and sort of the embedding manifold of liquid water? Okay, so that's the question that we asked. And so over the last couple of years, through a collaboration with Alessandro Laio and Alex Rodriguez, who by a coincidence is actually attending a PhD defense here yesterday. So I met him at the residence hall, which is kind of interesting. And so he's a physical chemist who's gone rogue and become a data scientist. And so we started talking a lot. And so I got very interested in trying to use or adapt what I call unsupervised learning approaches with the quotes, because I learned that nothing is ever unsupervised at the end of the day. And so the protocol is summarized here. I will just sort of give you a bird's eye view of what it involves. The first step is defining local environments, local atomic descriptors. And so these are very popular now in the neural network machine learning community. We use a technique called the smooth overlap of atomic positions, developed by Gabor Czanyi. I will tell you a bit about this in the next slide. These local atomic descriptors are then fed into a recipe known as the two nearest neighbor estimator for the intrinsic dimension. This is a bit like how you would estimate the fractal dimension of a data set. It's not exactly like that, but it's something like that. And then this intrinsic dimension is fed into a protocol that is basically coming from people in the statistics community, where they've come up with ways of constructing high dimensional probability distributions with appropriate error bounds. Okay, this is because usually, histogramming in high dimensions is very, very difficult, right? And one of the big challenges is getting control on the error. So Alessandro Laio and his group developed this technique that allow you to get these high dimensional densities, probability densities, and therefore the free energies. Okay, and so that's the protocol. I'm going to share with you a couple of results that come from different types of water models. If you're not a water model novice, it doesn't matter. The first and the last one are, classical point charge type water models. The middle one is kind of the state-of-the-art water model in the field. It's a many-body polarization water model, but at the temperatures that we're dealing with, it doesn't matter so much, actually. Just a brief prelude to the idea behind this smooth overlap of atomic positions. The basic principle is you put Gaussian functions on all your atoms, and you basically do a bit like what you do in quantum mechanics, but now on atom densities. And so you can expand your densities in terms of radial and spherical harmonics, and you can combine this into a spectrum where you get very high dimensional spectra where the coefficients of the spectra give you a lot of intricate detailed information about the local environment. Okay, so that's our agnostic, or as close as possible, agnostic descriptor of the local environments. We're going to use that to sort of address questions about the discrete notions that I introduced to you earlier. And the other nice thing about this is with these local atomic descriptors, you can now go back and really ask, how do the environments, for example, in water, near a protein, near an interface, how do they compare with milestones like ice, in a way where you don't need to define cutoffs in the way that you do with the order parameters that I showed you earlier on. Okay, so let me show you some data, some results. So the question is, what is the intrinsic dimension of water? And so there are three things here. We first looked at the intrinsic dimension of water, looking at an environment of about 3.7 angstroms, only focusing on the oxygen atoms. And the ID that we get is 5. I said, what is the meaning of this 5? 5 means that you need at least 5 degrees of freedom, 5 directions in which to describe the fluctuations of the local environment. So you cannot just use 1 or 2 independently. You have to look at 5. I haven't told you what those 5 are yet, but you need 5 of them. When you add the protons, you increase the intrinsic dimension to 8. So you gain 3 more degrees of freedom. So you need at least 8 variables to describe all the directions in which the local environments can fluctuate. If you expand the size, so you go from, let's say, first shell to second coordination shell, the intrinsic dimension grows to by about 1. So not too much of a surprise, right? The orientations that are induced by the positions of the protons sort of add more information, so to speak, when you use the intrinsic dimension, because it goes from 5 to 8. So you increase by 3, and then only by 1 when you increase the length scale. Okay, so now I have an intrinsic dimension. Yeah, please.
Is that number an integer? Or could
No,
it be a real number?
Yeah, no, it can be, it's a real number. It was like 5.1.
Okay.
I should have an approximate sign there, but yeah, no, there's no news, yeah. Okay, so now I have an intrinsic dimension of the embedding manifold in which the real local environments of water live in. And now I want to ask, can I recover any evidence of 2 states, low density, high density of water? Okay, so that's what we do. And okay, well, as you can imagine, visualizing anything in 5, well, anything beyond 3 is very difficult to do. And so what we do is just for visualization purposes, we use this technique called UMAP, which allows you to project in 2D, but the message remains the same. Basically, the free energy landscape of water is very broad and flat, with lots of small ripples on the order of kBt. And the analogy I like to give, which takes me back home, if you've ever traveled to East Africa, if you haven't, I recommend that you do. It's this big crater in Tanzania. It's called the Ngorongoro crater. And essentially, this Ngorongoro crater is a big crater. It's very flat with lots of ripples at the bottom, and then it rises very steeply on the sides. So looking at the free energy landscape, there's no evidence of the type of LDHD that people talk about. Okay, so let's dig in a bit deeper. So we can basically now drive along our crater and try to see if we can find any correlations or relationships between something that may look like a high density and a low density liquid. And so to help you with the analysis that I'm going to show here, we define 2 types of environments. So defects, so like you would think about in solid state physics, and non-defects, which are all waters that obey ice rules. Okay, and I can construct the local, let's say, densities, the Voronoi densities, for water molecules that are, let's say, at the bottom of the crater, and water molecules that are somewhere high up here in free energy. And what this plot is showing you is that, okay, at the bottom of the free energy minima, you have things that look more like high density environments, but they come from a mixture or a spectrum of lots of different things. Things that look like ice, so they're obeying ice rules, but also defects, as you might expect in a disordered liquid. And again, also when you move up high in free energy, even though it's on average, let's say, low density, as you can see from the shift here, the environments come from a big spectrum of lots of. So discrete two-state notions at room temperature, at least in my opinion, are not meaningful. Okay, so that's room temperature. Okay, so this basically described what I was trying to say in words. But we can say now, okay, well, let's go to the supercooled regime, where there's been a raging controversy over the last 2 decades. And if you haven't already, I highly recommend you read this very interesting perspective. This was an interesting war that took place between the East and the West Coast of the US. So David Chandler, the late David Chandler and Pablo de Benedetti, which ended up basically in a coding bug of the Berkeley group. And so the sort of the swing is swung now to the Benedetti camp, okay? But the question still remains, is are there, can water models that exist, can they reproduce or give a signature of a second liquid-liquid critical point? And so a couple of years ago, De Benedetti and Shortino teamed up, and they showed that in realistic point charge water models, they were able to see very long microsecond timescale simulations, fluctuations between a low density liquid and a high density liquid. And these are these histograms that show these sort of approaching the critical point. And what they say is that the critical like fluctuations that they observe in these simulations are reminiscent or consistent with a 3D Eigen universality class. So this is, the statistical physicists like this type of stuff. And again, the interpretation of the high density and low density liquid here come from these two-state local structures. And so we decided to say, well, let's take our agnostic approach. Let's see if we can map macroscopic high density and microscopic low density into these local structures. And so we do the same thing. We soap descriptors. And if I repeat the same exercise that I showed you for room temperature water, basically, we don't get to local minima. So local environments do not report on the global density. On the other hand, if I define a new type of descriptor that averages over a longer length scale, then you begin to see the emergence of the two peaks. And so what this is telling you is that basically there's a lot of heterogeneity in these macroscopic HD and LD phases, which you cannot directly link to local structures. And you really have to look beyond the local structure on a length scale of about a nanometer to really define or see. Yeah, please.
In the simulation on the left, I mean, it seems as if the whole system is going from low density to high density.
Yeah, it is.
The original proposal is that they live in coexisting.
Yeah, so this is a good point. These are the only way you can do these types of simulations is forcing finite size effects to allow. Well,
is that what you mentioned yesterday, that they took very low pressure?
Yeah.
Okay, again, I think probably one should have pointed out when presenting it, because if you put very low pressure, you are forcing things to behave differently.
They do, okay, besides this, they also do an NVT constant density simulation of a gigantic box, which are, they claim, very, very close to the critical point. They measure the structure factor there. They measure the scaling of the structure factor, the correlation length in these simulations, which appears to be consistent with the 3D Eigen thing, which they also infer from these simulations. So take it however you want, but yeah. So there are several ingredients here that they, from different types of simulations, that make them suggest this point. Okay. but let me say that my contention is, well, we're taking their simulations and analyzing them. And my contention is more that each of these macroscopic phases, and we've also done this now for these very large box simulations, there's no evidence of any local structure as a state, local structure as the way people think about it. You have to look at, so the reason why this happens is there's a huge heterogeneity, even in the macroscopic LDL and HDL phase in the local environments. Only when you look at some critical length scale, I think this makes sense. You have to look at things when you go to those temperatures on a much longer length scale. And so I would argue that local structures, the notion of a local structure, even in the supercool regime, is we should think about it, whether it's true or not. I don't say I'm right. I just tell you that this is what we're seeing from our analysis. Okay, so that's supercooled water. Another thing that, so just to give you a hint, that we're using a very similar sort of approach to try to ask the question which I proposed, which is when you have a proton in water, the proton does all sorts of weird things. It moves around with something known as the Grothus mechanism. So it's very different from hydrodynamic diffusion. Okay, so it's actually able to break covalent hydrogen bonds, and so we said, okay, well, let's try to see if we can say something about, is it Eigen or is it Zundel? Again, I've gotten into this habit now of taking the entries run by other people. And so we do that, and okay, well, what do we see? Well, this is the fringy landscape of 2 molar hydrochloric acid. And what we find is that there's the minima of neutral water, the same one that I showed you earlier on. And then there are 2 other minima that appear to come up. One minima here is correlated with the charged, let's say, a defect. Okay, so, and in this minima, you have again a big blur and a mixture of Eigen, Zundel, I don't even know what to call them. There's just a mix of many things. And so, and the other minima here is a neutral cluster, which basically are water molecules that are neutral but are defective. Okay, and so the presence of the charge defect enhances the concentration of this guy. And this is something we're still trying to understand. But going back to my Ngorongoro crater analogy again, the way I think about it is that you've got this fringy landscape where, besides low density like environments that come from a spectrum of things, you've also got these charged topological defects. And this charged topological defect is really a mix of Eigen and Zundel. And the question is now, how do we go back and reinterpret IR and Raman spectroscopy in the language of fluctuations in this let's say, free energy minimum? Okay. Okay. Well, I think I will skip this, but basically this goes back to the point of being able to compare with milestones. And the take-home message here is that essentially there's been a lot of experimental work where people measure the structure of the proton in clusters. And they use those clusters to make interpretations of the proton in the condensed phase. And what we're arguing here is that basically that it's very, very dangerous to use gas phase or cluster geometries to make inferences about what happens in the condensed phase. Okay. So now let me switch. If there are questions on this part, I'm happy to take them now or continue till the end. Yeah, please.
Yes. So a couple of questions. So these microsecond simulations, are these MD simulations with empirical potentials, or?
Yeah, it's TIP4P ICE, TIP4P 2005. Those are the 2 water models that they use. So they do very tons and tons of long, tens of microseconds, and then combined with some enhanced sampling, the histogram, weighted histogram analysis method that allows them to compares, use statistics from different thermodynamic ensembles and construct the free energy.
And what is the number of molecules?
In they do 400, 1,000, and 5,000.
Not too big.
It's not too big. I agree. It's so you know, in order for them to see, in order for them to go to this time scale, they are forced to do small boxes, but then they do like finite scale, finite size analysis. Of course, with larger boxes, shorter simulations, and yeah.
And also when you are calculating the free energies, right?
Yeah.
Landscapes, how you estimate the free energy? Because it's not so trivial in molecular dynamics, right? Or
So no, it's if you know the order parameter, this is the key. If you know the order parameter, it's, I would say, semi-trivial. Because basically it's a question of computing the density of your order parameter, and it's minus the logarithm of that gives you essentially the free energy.
okay.
The challenge is how to do it correctly in high dimensions and with proper control on the error. And okay, that's
If you
yeah.
considering the fluctuations of the protons and so on.
Yeah.
So let's say the vibrational contribution, the entropy and
Yes. For these simulations, definitely, because these are with full-blown ab initio. These ones by Shortino they have rigid body as well as flexible. But yeah.
Yeah, it was not totally clear to me, going back to the question of whether it's an integer or it can be
yes.
any like
Yes,
other
exactly.
number. How you derive the number of intrinsic dimensions?
so
I wonder if it's something like after you have your feature vectors,
Yes.
you use some sort of like principal component analysis.
No, so not principal. One could do that, but so the idea is the following. So for every data point, you can measure the distance of that data point to its first and second nearest neighbor. It turns out you can show mathematically that the ratio of the second and the first nearest neighbor, the cumulative distribution of that, if it is a Pareto distribution, which is commonly the case of these, can be related to the dimensionality. So that's how it comes from. And so it assumes no information about linearity, for example, that you would need in principal component. It turns out that if you use principal component analysis, you basically have to define by eye where the spectrum kind of has a gap. And if you if you tweak your eye a little bit, you can find similar ones that are consistent with the intrinsic dimension. But yeah. Okay, good. I'm happy. I'll share the paper with you so you can see the technicalities. Okay, so maybe let me try to tell you a bit about the second part of what I want to tell you, which is hydrophobicity. And this is sort of a classical picture in physical chemistry developed by Chandler and Pratt and coworkers, where the idea is the following. So if you have a small hydrophobe, the free energy grows as the volume, okay? And then when you get to some large critical length scale, you reach the macroscopic limit and things behave or grow with the surface tension. And so there's this competition between volume at short length scale and surface area. So the way Chandler draws this is, a very sharp transition of two length scales, and it's a theory that's been developed thinking about idealized spherical geometry. Okay, and so we sort of began to ask the question, well, what about non-spherical shapes, as would be the case in everything in reality? And so from the point of view of the thermodynamics, what one typically does is you have a simulation like the one I showed you, and there are elastic sort of modes, fluctuations, And then eventually you will create a cavity in the liquid, and you can count the statistics of creating these types of cavities and therefore get the free energy, for example. And so we started asking, well, how about non-spherical shapes in liquids in general? Okay, so I don't have time to get into the technicalities here, but we use a technique known as Voronoi, a variation of Voronoi voids that allows us to construct exotic shapes in liquid water. I will just focus on liquid water here because the methane is not relevant for the discussion. And what I want you to take away from this picture is the following. Spontaneous fluctuations in liquid water at room temperature are creating lots of interesting shapes. So these are shapes that we've carved out from water, and they are quite sizable in their magnitude. So you can fit basically up to about 4 to 8 water molecules in these empty spaces that have all these weird shapes that come up just by spontaneous fluctuation. And so the question is, what we started staring at these objects, and well, maybe we got a little bit too creative, and we said, well, okay, maybe this seems like if you stare at the shapes of these voids, they kind of resemble the shapes of small molecules or polymers. So, and so we can do this on the computer, and so we did. So we sort of asked ourselves, can we find shapes in bare liquid water that resemble the shapes that are taken on by a polymer? And so we use again this SOAP descriptor in another way. I won't tell you the details, which allow us to compare the shapes of the polymer to the shapes of these voids. And let me start by the anecdotal sort of suggestion, which is these are simulations here of Leonard Jones polymer, 10 beads, hydrophobic, resembling decane. And we ask, can we find a shape that resembles that in liquid water? And well, funnily enough, you can see that there are shapes that are forming in liquid water that are sort of similar. But, you know, no water does not have a memory. And, you know, of course, the timescales of the fluctuations of these things are on the order of hundreds of femtoseconds. Okay, so it's a very short-lived sort of object. Okay, but this doesn't tell you anything about thermodynamics yet. And so what we did was we constructed, so this was the original polymer that I showed you in the previous slide. This is another one with a bit of a branch, so it looks like a cat or a dog, depending on your preference. And we asked ourselves, what is the free energy of solvation of this polymer? And so we can use a technique known as thermodynamic integration. We get about 20 kilojoules per mole. So that's the free energy of solvating decane in water. And then we can go back to our simulations of just bare liquid water and ask, what is the free energy to spontaneously create one of these voids? And it's really curious. Basically, you don't need to do a lot to the water network to host a small hydrophobic polymer. You sort of get it for free by spontaneous thermal fluctuation. Okay, so that's sort of the take-home message. And let's say the difference between this number of 20 and 17 is basically that, of course, when you have the real polymer, you need to blow a bit more air into the cavity to make it happy. Okay, and so that's where you get that basically on the order of kBt contribution. Okay, so that's small polymers. So we said, let's go back and try to see protein folding, polymer, hydrophobic collapse of a polymer. So we did simulations of different types of polymers of different sizes. And what's interesting here, what I want you to take away from this is even when you get to very large folded polymers of the size of 100, you are still quite, you are still quite far away from the hard sphere limit of a spherical cavity. And so this is sort of reflected here, where I'm showing you the cumulative distribution of the branch density. So we have a way to identify these branches and measure their density. That's what you get for a hard sphere. So that's when the system is really, you're at a limiting case where you really have a quasi-spherical bubble. And even these large folded polymers are quite away from that. And so there's a rather slow transition in that phase diagram that I showed you, the crossover of volume to surface area from the surface tension regime. And we believe that this is due to the presence of these non-spherical branchy voids. Now, in the community, there's been a lot of discussion on how the hydrophobic effect is related to an entropic contribution coming from disordered and ordered water around a hydrophobic polymer. And the question is, so where is this type of entropy manifested? And this is, I think, still an open question and not clear what the answer is. But if you measure what is the tetrahedrality, the order parameter that I introduced you earlier on in the talk, and you measure the tetrahedrality of water around the polymer, the different sizes, you see that it looks like there's some shift going on here as you go from the unfolded to the folded state. However, if you start to look at the water around this branchy void, so you use this as your surface, basically, there's very little changes. And so what we think is going on is that, number one, first of all, order parameters, one-dimensional order parameters that are used to make inferences about entropic effects are, say, questionable. One has to re-examine them. And secondly, there's rather subtle and close to very little differences if you really start looking at the water structure around a polymer as it undergoes the folding and unfolding. So maybe there are other smarter ways in which one can use other order parameters to really interrogate the entropy. But this is something that we're still, let's say, thinking about. I just showed this last one here as an example for the more chemistry inclined people, because everything I've shown you up to now are toy model Leonard-Jones polymers where there's no chemistry. And rightly so, you may ask, and you should ask, well, if I put real chemistry, real charge, how does this affect the cavity shapes? And so we've looked at, all the amino acids, trying to study the properties of the cavities. And what we currently have is essentially that if we try to build a linear regression model, so something really simple, between the void shapes, so we have order parameters that measure the shape of the voids, and the free energy of solvation that we get from experiment, we aren't doing so bad. Okay, and so take-home message, in the canonical classical, actually, let's say nucleation, solvation theory, we think about volume and surface area and that competition. And what we are claiming is that there's a regime there where there are other variables that one has to look at, which are, the branchiness of the shapes of these cavities. And this is kind of curiously related to solvation thermodynamics. Okay, how much more time do I have?
5 minutes.
5 minutes, perfect. So I'll basically rush through this. So another sort of topic that we've been exploring recently is this, what we call the blurry boundary between oil and water, so hydrophobic water interfaces. I'll just say here that yet another raging debate in the field is why oil droplets in water under the influence of an electric field move to the positive electrode. So they appear to be negatively charged. And there are many people in the community who've been arguing for that they are negatively charged hydroxide ions that bind to the hydrophobic surface. So we've been trying to challenge this idea. And basically, we've been thinking about how hydrogen bond asymmetries in the hydrogen bond network, how they affect charge transfer. And so if you go back to my free energy landscape, there are defects that form by fluctuations, and these defects will have an asymmetry in the hydrogen bonding, and this asymmetry leads to some asymmetry in the electron delocalization of the hydrogen bond network. And so these types of water molecules basically, I would say, can take on some interesting charged or dipole properties. I'll skip this and just tell you that if you have oil, so this is really boring oil, right, in contact with water, we have evidence from calculations and now also from experiments that there's some partial charge transfer from water to the oil, which means that there's some highly non-trivial interactions, electronic properties, electronic polarization that's happening between water and an oily molecule. And sort of let's say the picture that we have is essentially that if you have a hydrogen bond in water, that's about 10 kBt, right? If you put decane in contact with 10 to 15 water molecules, electronic polarization and charge transfer, you can lump them together if you're a physicist. That basically is about kBt per interaction. So you can essentially get something like a hydrogen bond in strength because of this sort of collective effect of electronic polarization involving the CH hydrocarbons and the water. This was proved by collaboration with Sylvie Rocchi at EPFL, who did vibrational spectroscopy. And one of the things we're trying to explore now is whether this persists for hydrophobic molecules in the bulk and not necessarily just at interfaces. Okay, so let me wrap up. What I tried to do today is to tell you about simplicity on one side, projections, which are at the heart of a lot of our interpretations, a lot of our models, because they allow for easy bookkeeping, easy cataloging. And the reality is this complex mess, okay? Which I think is still beautiful to understand. And I will stop here. I will acknowledge the various people who've been involved in this collaboration. Eddie, Uriel, and Khatere are still three people in the group. And let me do some shameless self-advertising. We have openings for postdocs and PhD positions as part of a project on hydrogen bond network fluorescence. And a last shameless self-advertising. We have a partner institute in Rwanda, in Kigali, in Africa. If you're interested in helping, contributing to teaching, mentoring students there, definitely get in touch with me. Okay, thank you very much.
Thank you very much for this wonderful talk, Ali. Time is open for questions. There might be also some questions online, so please, those of you who are online, write in the chat or raise your hand, so I know that you have some questions.
Going back to the entropy
Yes.
thing, is there a chance that these tetrahydrality that you're feeding into the analysis doesn't quite capture the enveloping? So maybe it's very good for the bulk structure of water, but not quite for the ordering which takes place on the surface of the body that is being folding or whatever.
That's a great point. So I think yes, I think that's part of it, and part of it to what you describe as the enveloping is that you need to define what the right envelope is. And well, what we tried to do is we said, okay, we think the cavity shape is a better envelope. it's a better surface to look at. When we look at that surface, local tetrahedrality, we don't see a difference. But it may well be, and it would not surprise me if there was something more, one has to look along the envelope on a longer length scale. But all I will say is that, yeah, the local structure that people, as you say, they use in the bulk, it's been used in the bulk and try to apply to an interface, I think is problematic. So yeah, I completely agree.
Other questions? We have many of them during the talk.
Well, just to continue.
Yeah, sure.
As we mentioned, if you look, just you treat the water as a dipole and you look at the orientation and distribution. So in the bulk, it is isotropic, but on surface, it would not be isotropic. Why you would not want to assign entropy to the reduce entropy to the anisotropicity of interfacial water?
That's a good, I think in principle, one could do it. All I will say is that I think, so if one could define an anisotropy in the dipole distribution along the right envelope, that's corrugated and rough. So in the context of an interface, flat, except I agree with you. It's to me, it's simpler and easier to define that.
But to the tangent of the surface.
For the case of the polymer, with all its corrugations, I think sure one could define something similar. But I have to say, what we discovered, okay, for the oil-water interface is that it is only within the first 2 angstroms, 1 point really only close, where you see anisotropy. And then immediately after that,
I think many people would agree with you.
Yeah. And so if there's a way to convert, yeah, I think one can make heuristics about that and relate it to entropy. But to me, I think there has to be something that looks at the non-locality, because there are correlations at the interface that are longer range. And somehow that has to be taken into account.
If you attribute the changes to the surface area, then it makes sense that it is only local, because that's actually a reflection of the surface area.
It's a surface area of a highly rough corrugated object that's not local, right? So, right, because let me go back. No, for that. So this object here is a surface area of a highly non-local corrugated thing, and so to me, by construction, the surface area is non-local, right?
Yeah, well, I mean, okay. It is local from the interface. From the hydrophobic solute, at least the center.
You mean
It is, well, maybe we're talking about the same
maybe we're talking
thing.
about
maybe.
But maybe okay. I think what you're saying is basically that the chemistry or the perturbation that the interface of solid is a local thing. But then
if it's big,
the response is not local. This is what I would say. The response is it's what delocalized, it's spread, and then there are correlations between sites that so maybe it's semantics. I don't know.
Maybe
it could,
Yeah, I think this could be a good point, let's say this, to end the.
Yeah, it's a specialist discussion, I
Yeah,
think.
yeah. This is a more specialized discussion, so I thank you very much again, Ali, for
No,
this.
thanks again for your question. Thank you. Thanks very much.
And by the way, maybe I get the wrong impression. At the end, but I mean, what you said, I mean, the second critical point
Yeah.
of water, I mean, maybe there is no thing, there is no basis to observe. Maybe, I think it is there. Though the conditions are too
Yeah,
strange
I think
to start to say that it's.
I agree. Yeah.
That's right. I mean, yeah, maybe.
The simulations are the simulations. They have an observation. It fits a model. I see.
Yeah, exactly.
The physics is like. So, okay, check. As we discussed yesterday, negative pressures. So a grain of salt.
No, but yeah, I mean, I think, yeah.
That time scale,
Yeah.
that temperature, right?
Yeah.
You know, I mean, it's like 100 and one scale. Yeah, exactly. And then it happens, too much happens for something that. I guess the pressure can just determine like the
Exactly,
behavior.
yeah, exactly, yeah.
But you wouldn't expect such, I mean, at that temperature, you shouldn't have frozen molecules, period, right? 170
That's
Kelvin.
super, yeah, exactly.
And there's very large density fluctuations on the microsecond time scale, which are sort of surprising.
Yeah, so they do them because these are, let's say, NVT, some, no, these are NVT, sorry. Yeah, these are first NVT. I forget which pressure they're doing them at.
Yeah.
But, you know.
Yeah, that's right. This is NPT. Otherwise, you would think
otherwise you-
distance maybe.
In fact, and this is what they argue.
Okay,
They argue, we took a large box,
Exactly.
we do NVT, we look at the structure factor. And they see long range correlations, and the idea is that they're domains of coexistence. But I don't find them. I think they are nucleating ions. Even though they claim that they
That's
argue.
on the point of nucleating,
Yeah, the point-
nucleations and dissolving.
So